Hey folks, how does an MCP server handle 10,000 requests per second? Most setups start simple, a single server handling requests. Our agent sends a query to the MCP gateway, which routes to a single worker. This one to one mapping works for low traffic. The agent sends a request to the gateway, which forwards it to the worker. The worker executes the tool and returns the result back. This works fine for one request. But when load increases, that single worker becomes a bottleneck. But that server fails at scale, let's see why. At 100 requests per second, the worker's latency spikes from 10 ms to over 200 ms. The single worker can't keep up with the flood of queries. Each new request adds to the backlog. Latency grows linearly with queue depth. The worker becomes the bottleneck for the entire system. We need a smarter architecture. The first fix, cache common tool results. We add a cache layer to store frequent tool outputs. When a query comes, the worker checks the cache first. If the result is cached, it returns immediately. For repeated queries, the flow is much faster. The agent sends a query, it routes through the gateway, and the worker retrieves the result from cache. But for unique queries, the cache misses. The worker must process the original call. Cache helps, but not for unique queries. Here's a typical request lifecycle with the cache in play. The agent sends a query to the MCP gateway, which routes it to a worker. On a cache hit, the worker fetches from cache and returns the response in just 2 milliseconds. On a cache miss, the worker must compute the response itself, taking 50 milliseconds. With an 80% hit rate, average latency drops to about 12 milliseconds. Each request costs 0.001 hours in compute. But tools with side effects can't be cached. Let's zoom into the worker to see how it scales internally. It maintains a queue for incoming requests, a thread pool for concurrent execution, and a rate limiter to control flow. A single request costs about a tenth of a cent in compute. At 10,000 queries per second, that's $1 per second or $86,000 monthly. But traffic spikes can overwhelm a fixed pool. Watch 3 requests arrive in quick succession. The queue absorbs the burst, delaying them until threads free up. The rate limiter prevents too many queued jobs. It rejects a request when the queue is full, keeping the system stable. After the spike, the queue drains and the worker returns to steady state. The cost of compute remains predictable. With proper buffering, the worker handles spikes smoothly. But sometimes the tool takes seconds should the agent wait. In synchronous execution, the agent sends a request and then blocks. It waits for the worker to finish and return a result. This ties up the agent thread and it cannot do other work. With asynchronous execution, the agent sends the request and gets an immediate acknowledgement, like a request ID. The agent continues processing other tasks. When the worker finishes, it sends the result back through the gateway. The agent then picks up the response. Compare the two patterns. On the left, the agent is blocked, waiting for the worker. On the right, the agent is free. The worker thread is also freed after sending the callback. This reduces thread contention. For long running tools that take seconds or minutes, the synchronous path wastes resources. The asynchronous path lets the agent and worker handle other requests in the meantime. Async wins for long running tools. Here's the async flow in action. The agent sends a query to the MCP gateway. The gateway returns a job ID immediately. The gateway routes the job to a worker. The worker begins processing. It fetches data from the cache. The cache returns the data. The worker completes the job and sends a callback. The gateway forwards the result to the agent. This asynchronous pattern allows the system to handle many requests concurrently. Now we have a scalable MCP server. Putting it all together, at 10K QPS 20 ms PN9 costs 0.01 miles per request. The agent sends a query, the gateway routes it, the worker fetches from cache, and the response returns. The cache delivers 20 ms P99 latency. And the total cost per request is just 1 cent. That's how you scale an MCP server. We started with a single MCP server, saw it fail at 100 QPS. added a cache to reduce latency, dove into the worker's internals, and switched to async for long running tools. The result, a system handling 10,000 requests per second at 20 EMS P99 under a cent per request. That's how it works under the hood. Subscribe for more system design breakdowns. Catch you in the next one.